Hello, everyone. Welcome back. This is the review of the last lecture, which was the first lecture on Bayesian networks, construction, inference, and learning. And it goes in a way beyond simple supervised learning because we are modeling a complete domain with several relationships between variables. So here's an example, one of the standard examples from literature, and it's a diagnostic example. And you see different layers. So up here is the disease layer with tuberculosis, lung cancer, and bronchitis. And the patient can have several of those diseases, or none, or just one, or just two. And on the bottom here we see the symptoms, maybe a positive X-ray, so eine positive Röntgenstrahl, Befund, dyspnea, which is shortness of breath, or Atemnot, and then here's an intermediate node which simplifies the modeling. But essentially we have three layers: the diseases, the symptoms, and then preconditions which influence the probability for getting a disease. So smoking might increase your probability of getting bronchitis or lung cancer. And this is, so the expert has to define the relevant variables. So visit to Asia, smoker has tuberculosis, lung cancer, bronchitis, X-rays, dyspnea. That's the first thing, and then the next thing is the expert has to define the causal dependencies, so the direct causal dependencies. Visit to Asia changes the probability of tuberculosis in a causal way, and smoking in a causal way changes the probability for lung cancer and bronchitis. Of course, there are also indirect causal dependencies between, for example, smoking and positive X-ray, which is mediated by other variables. And to really analyze causality is a different topic, not really addressed here. But this is the basis. No? So if you want to understand Judea Pearl's approach to causality, you have to have a good understanding of Bayesian networks before. And one thing is the Bayesian network qualitatively depends on a factorization of the probability distribution. So you need the probability of each variable given the parents of the variable, and then the joint probability is simply the product of all these probabilities. So you would have to specify the probability that somebody has lung cancer, given that this person is a smoker, but you also need to specify this probability given that the person is not a smoker, and so on. And then this formula, which is based on the factorization of probability distributions, lets you build the complex, the complete probability model for the whole domain. And in inference, we are making the distinction between the variables which are measured. So set is called x super m. And the one variable we want to get information about, the query variable, and the remaining variables, which is this x super r set. And the conceptually or theoretically, the inference is pretty simple, and we have discussed this already. So in the first step, we write down the joint probability distribution from all variables, x1 to xm, and then you get rid of the ones which you are not interested in, so the ones which are not the query variable and also not the ones which were measured. And this is called, we discussed before, marginalization. So you have to build a big sum over all the states of all the variables which are not of interest. And then you get the probability distribution out of the query variable you're interested in and the measured variables. And then you do one more marginalization because you also need the probability for the measured variable. So you have to integrate out the xq, which we're doing over here. And then what we're interested in is the probability of the query variable given all the measurements and all the measured variables. And this is just the definition of the conditional probability distribution. Is just the joint distribution of query and measure divided by the probability of measured. But you can do it for any set. This operations for any set of measured variables, and you can do it for any set of query or any individual query variable. So you can use one Bayesian network to cover many different situations with many different set of measured variables and different query variables. So based on this formula, you could, for example, in our example, calculate the probability of smoking that somebody has dyspnea, or the other way around, what's the smoking probability of dyspnea given somebody is a smoker, or what is the probability of a positive X-ray given that somebody visits Asia but is not a smoker. All these fancy questions can be answered by following this simple mechanism. The main difficulty why the story is not quite so simple is this marginalization over all remaining variables. And this can be a pretty large sum because the sum is exponentially many terms as a number of unknown variables. So 2 to the number of size of xr essentially. And this can be too large. And that's why we are talking about belief propagation and approximate inference, because we want to get this to be calculated more efficiently. Then we went to an example. I want to go through this again, how you design it. This is a bigger network, which, as I said last time, it was sort of a breakthrough because this was an Intel troubleshooter network from Microsoft, which was a big success at that time and got a lot of companies to also join this research area. This is the one. Yeah, so inference, so this essentially this marginalization operation is very simple when you're having no loops. You're not allowed to have loops when you follow the directions of the arrows, but here you also don't have a loop if you remove the directions of the arrows. And in these networks, inference is quite simple and efficient, and you can use an algorithm called belief propagation, because essentially it's the evidence or measured information about measured nodes is sort of propagated through this network in a pre-described way, but it's also very efficient, and you only have to propagate everything once down and once up. So that's nice. And so we went through the example of the Markov network, and then we said in general networks without loops, we can generalize these concepts. So you have all these messages, the lambda message and the pi message. So the pi message goes in the direction of the causality, and the lambda messages go in the opposite direction. And every information only has to be propagated one time to the network according to some order, and then you have updated all the rules, all the nodes, and you can calculate the probability of any node given the evidence. Even if you're only interested in one node, you get all of them for free and in one big sweep. And yeah, this used this, okay. So this was the inference without loops when you take the direction of the arrows away. But not every. I mean, there are a lot of Bayesian networks which have loops. So we also have to know how to deal with them. And the simplest way is to do belief propagation, despite the fact that you have loops in your network, which is not exactly correct in some sense. You cannot really prove what this will converge to, but it gives good results in many cases, and this is called loopy belief propagation, and is sometimes applied in networks where proper inference is unfeasible because of the size of the network. And surprisingly, it's used also as a loopy version in the decoding of turbo codes or low density parity check codes. But there's also like a correct algorithm, which is the junction tree algorithm, and that works sometimes. In particular, I mean, the idea is that you have here, for example, is a loop. If you take the direction of the arrows away, you can go across here, around here. So the idea is to cluster variables, for example, Mary and Susan, to make into the Mary Susan variables. So these have two states each. This then has 4 states. And so the number of states of this variable becomes larger, but the advantage is that the loop disappears and you can do belief propagation. That's the basic idea. And finally, was the last thing we talked about designing a Bayesian network, and the problem is you have to query the doctors, for example, in the medical domain about all these conditional probabilities, and it's not as difficult as you think, and we don't have to be extremely accurate. So if you get it, the 0.1 error is not a big problem. So if it's 10% or 20% or 20% or 30%, of course, it should be. So if it's 1% or 0.1%, that can be a bit different. So this 10% is wrong. It has to be in relationship to the numbers. And so it should be, it can be 10% off or whatever of the number, not 10% difference. Or if you say 99, very different from 99, 99% from 99.999, it can lead to very different results in relation to the true number. The estimated number should not be too different in terms of the proportion of the two numbers. But still, sometimes you're asking for too much, and this is often the case in diagnostic Bayesian networks, where you might have a symptom like dyspnea, and the symptom can be caused by many causes, many different diseases cause dyspnea, or many diseases cause fever. So you have one node with a lot of parents, with a lot of errors going into this node, and then it's in principle you would have to ask the expert about all possible combinations of the parent nodes, and for each combination the expert needs to give you a probability, and that's impossible. So you're making simplifying assumptions, for example, that if you have one disease which gives you let's say fever with 50%, you have another disease which gives you fever with 50%. If you have both diseases, you will get fever with something larger than 50%. So they shouldn't cancel each other. They shouldn't. If you have two diseases, you shouldn't. The conclusion should not be that you don't have the fever, or the fever probably goes down. And one approach, which is sort of the basic realization of this idea, is this noisy OR model, which essentially implements what I just said. So you have to give a probability for these Q numbers, which is the probability that you have no symptoms when you have the disease, for each single disease. and then the other diseases are all false. And with that number, then we have a combination rule for giving you the probability that you have the symptoms given any combination of parent nodes, and it's 1 minus this product of the Q's, where you have to know that if, of course, if Q equals 0, then this is just the 1, so it sort of drops out, and this only plays a role if you have the disease. So this has exactly this effect, but it's an approximation in the modeling, and there are also other similar combination rules, which I don't present for shortness of exposure. So that was sort of the review from last lecture, and we will continue with learning integration networks. Thank you very much.